In this experiment, we verify the Curie Weiss Law for a ferroelectric material in the paraelectric range. Ceramic capacitors have a dielectric made of a mixture of oxides which have a Curie temperature near 20 degrees centigrade. This is done so that the capacitance will be large for a very small volume of the material because the dielectric constant will be large near the Curie temperature. About the Curie temperature, we are in the paraelectric regime. So, as the temperature increases, the dielectric constant comes down and the capacitance value comes down. So we can measure the change in capacitance with temperature and plot the reciprocal of the capacitance against temperature. We will get a straight line with a positive intercept on the temperature axis. This intercept is the Curie temperature, and the capacitance can be fitted to an equation, a constant by T minus theta. This is called the Curie Weiss equation. To show that a polymer capacitor does not behave like a ferroelectric, we have on this insert a polymer capacitor on one side pasted with araldite and a ceramic capacitor on the other side pasted with araldite. The two capacitors nominally have a capacitance of 0.1 microfarad at room temperature. The capacitor leads for the ceramic capacitor come to the red and orange terminals, for the polymer capacitor to the red and orange terminals on this side. Between the orange and green terminals, we have connected 1 K at room temperature, and the red and red terminals are connected together and the green and green terminals are connected together. The two blue terminals are the terminals for the platinum thermometer. I put this insert into the furnace. I connect the thermometer leads to the two terminals marked platinum 100. Then this indicates the temperature of the two capacitors. I connect the output of a signal generator to the red and green terminals on one side. On the signal generator, I adjust its frequency to be about 1 kilohertz and its amplitude about 1 volt. I can measure the AC voltage across the ceramic capacitor by connecting a DMM between the red and orange terminals. So I get a voltage of something like 0.913 volts across the ceramic capacitor. I measure the voltage across the resistance by connecting the same meter between the orange and green terminals. I get a voltage of 0.477 volts. The voltage across the capacitor divided by the voltage across the resistance is equal to the impedance of the capacitor divided by the resistance of 1 K. So by measuring the ratio of voltages, I can find the impedance of the capacitor, which is 1 by 2 pi multiplied by the frequency multiplied by the capacitance. So from the impedance, I can calculate the capacitance knowing the frequency of the AC. I can do it for the ceramic capacitor, I can do it for the polymer capacitor, because the same voltage is applied to this circuit and this circuit. I now switch on the heater, keep about 7 volts on the heater, close the furnace with a cotton wad. The temperature will increase. Every 5 degrees I measure the voltage across the ceramic capacitance, the voltage across the resistance. The next, that is at 30 degrees centigrade, let us say. At 35 degrees, I do the same thing for the polymer capacitor. Again at 40 degrees, I measure the voltages on the ceramic capacitor side. Thus, every 10 degrees, I can measure the capacitance of the ceramic capacitor and the capacitance of the polymer capacitor. I do it till the temperature rises to 700 degrees. Then I calculate the capacitance of the ceramic capacitor from the ratio of the voltages at different temperatures. I plot the reciprocal of the ceramic capacitor against temperature. You will get a very good straight line with a positive intercept on the temperature axis. If I plot the polymer capacitance against temperature, it will be nearly constant and will show a slight increase. On the other hand, ceramic capacitor value will decrease by a factor of 4 to 5 in going from 30 degrees to 100 degrees centigrade. This is a very simple experiment to verify the Curie Weiss law.